All right, we're going to be going through our last example in section 8.2.8.3 here, where we have a rational function whose degree in the numerator is bigger than the degree in the denominator. So we've been saying m is greater than n in this case. All right. First thing we're going to do here is factor the numerator so that we can use that to figure out if we have any x-intercepts or holes in the graph. Remember, if we have a common factor in the numerator and denominator, then there is a hole in the graph, as there was in the example previous to this. We had x minus 3 appear in both in the numerator and denominator, so there was a hole at x equals 3. We actually canceled those out, gave us a new function, and then we were able to put that 3 back in for x in order to find out exactly where that hole was. We found out that it was at 3, 12. Well, the only way that we'd have a hole in this graph, since there's only one factor in the denominator, x plus 1, is if there was an x plus 1 in the numerator as well. Well, it turns out there's not. We have x plus 2 and we have x plus 4 as our two factors, so there is no hole here. All right, so let's start breaking apart what we do know about this graph. I'm going to start with the vertical asymptotes first. Okay, and I'm even going to include the word holes kind of in this category, even though we know that there isn't one, because this is where we would talk about it if there was one. We know that our only zero that we're going to get from the denominator is -1. Okay, it's not a zero that is also in the numerator, so it's not a hole. It is a vertical asymptote, just like some of the earlier problems that we did. So we have a vertical asymptote at x equals -1, and we know that is a restriction on the domain. We know that -1 cannot go in for x in this function. So we never ever cross a vertical asymptote because of that idea, that it's a restriction on the domain. So there's my vertical asymptote at -1. Okay, the next thing we're going to talk about is the end behavior, or the horizontal asymptote, if there is one, or possibly a slant asymptote. Okay, so far in this category, we've only had horizontal asymptotes. Well, this time, m is greater than n. That means we're actually going to have a slant asymptote. The other telltale sign is if we look at that end behavior function, where we only look at the first term in both the numerator and denominator, we can simplify that. X squared and x simplifies to just x. That's a linear function. That means that we are going to have a slant asymptote. So that kind of tells us that same thing right there. All right, so how do we know what the slant asymptote is? We just have some random, slanted line on the graph here. Well, we find it by using long division. Okay, because that's what this fraction bar here means anyways, is division. So we're going to do long division to find the equation of the asymptote. To find the slant asymptote equation. Okay, now here's the nice thing. It is the quotient only. Okay, now we go a little bit more in depth about that as to why it's only the quotient in the next class. For right now, just know that we're going to do some long division, and it's actually going to be pretty easy because you can stop as soon as you are done with your quotient. Okay, so watch what happens here. We get x plus 1 into x squared plus 6x plus 8. We know is going to go x times, or in other words, I would multiply x by x to get x squared. All right, so now I multiply that x back through, and I get x squared plus x. Well, now we need to subtract. So I'm going to subtract that. I'm going to change that sign. So those cancel out. I'm left with 6x minus x, which is 5x. And if you want, you can drop that 8 down because it's long division. But look at, we're done here because all we have to do is say, well, how many times does x go into 5x? Well, it goes in 5 times, or I would have to multiply x by 5 to get 5x. That's the end of our quotient. We can stop right there. You don't have to multiply it through and find the remainder. The slant asymptote equation is y equals x plus 5. Let's go ahead and graph that on our graph over here as our asymptote. Y equals x plus 5. All right, all the difficult stuff that we're doing. Don't forget how to graph a y equals mx plus b slope-intercept line. We got a y-intercept of 5, 1, 2, 3, 4, 5, right there, and a slope of 1. So I'm going to just get a couple other points here, up 1, over 1, and then going down the other way, get a couple of points in, and then once I kind of recognize what's happening, I'll just go and draw an asymptote in here. Okay. So it goes through the y-axis at 5, and it has a slope of 1 over 1. All right, so that's our slant asymptote. Okay, now I'm going to take a second to show you what the graph of this actually looks like. And this is around the time where we're going to put this in our graph calculator to get a few more points anyways. But this is what the graph looks like. So you can see if on this graph I put in y equals x plus 5, 1, 2, 3, 4, 5, there's the y-intercept, and then the scale is off here. But a slope of 1 over 1 would look something like this because of how the scale is off. Okay, so here would be that slant asymptote there. You can see how it follows that asymptote going in either direction. All right, so let's go back to our graph here. And let's hold off on putting in our graph calculator for right now because we have two other important points that we can find. The x-intercept and the y-intercept. Okay, the x-intercept comes from where we get zeros in the numerator. Well, we already factored the numerator. Okay, you don't have to write this stuff all over again. We can just write what the zeros are from the numerator. They're -2 and -4. Set those factors equal to 0. Okay, so we have two x-intercepts. -2 comma 0, -4 comma 0. -2, 0, -4, 0. All right? I have a pretty good idea of what that function looks like over there. I know it's going to be doing something like this right here. I want to know where that point is right there, though, where it turns. In other words, that local maximum. Oops, I lost my -2. Okay, we'll find that on our graphing calculator. How about we put, and it might be the local maximum, I'm not sure. How about we put one more point on the graph on this side of that vertical asymptote? How about the value? Obviously, that one would be pretty useful right there, -3. Okay, if you put -3 in, and you can use this function if you want, you can use that function you want, or if this is the point you want to just put it in your graph calculator, I don't care. But -3 is pretty easy to put in because you get, if you put -3 and you get -1, you get 1, and then down here you get -2. So you have -1 times 1, which is -1 over -2, where you get 1/2. So -3 gives you 1/2, 0.5. So here we got it right there. Now, is that the local maximum? I don't think it is. We'll find that local maximum in a second. But what I am going to do is I'm going to graph this leg of this hyperbola here because I have a pretty good idea of what that looks like. All right. So the other point that we could find yet is the y-intercept. The y-intercept comes from letting x equal 0. Okay, remember, if x equals 0, all this goes away except for the constants. So the x-intercept is just, I'm just going to remind myself that it's, h of 0. Excuse me, the y-intercept is h of 0, which is just going to be 8 over 1, which is 8. So the y-intercept is 0, 8. There's 5, 6, 7, 8. Okay, there's my y-intercept. That's about the only point that I'm going to get on that side of the vertical asymptote. So let's put in a few more points on that side of the line as well. Maybe the points 1 and 2. Let's see what we get out of this. And if you haven't done so, put that in your graphing calculator. Go to your y equals. I've got it right here. X squared plus 6x plus 8 over x plus 1. It's going to be that green graph right there. And I have my graph on the 10 by 10 window, the standard window, so you just do zoom 6, but I've got this all over here too. So if you want to write down what we get for 1 and for 2, we get 7.5 and we get 8. So at 1 I get 7.5, and at 2 I get 8. I have got a pretty good idea here what this looks like. None of these are holes, so I can go right through them. Remember, a hole only occurs when there's a factor that's both in the numerator and the denominator. Okay, so the last thing that we're going to do here is find those local minimums and local maximums in order to find the range. because we want to name what the domain and range are. So on our graphing calculator, I'm going to find that local maximum right in that area first. So I'm going to go second trace to go to that calc menu, and I want to go to maximum number 4. Okay, and I need to scroll to the left to get that cursor to hop over to this asymptote on this side. And you kind of, if you lose it for a second, go back down here. If you lose it for a second, you can always use your values down here to tell you where you're at. Right now I'm at negative 7.5, but my y value is up there, so I know this is somewhere up here. So I'm going to keep going to the left, and there it is, and I want to be on the left of that local maximum, so I'm going to be over there somewhere. Hit enter. Now it wants a right bound, so I'm going to go to the right of that maximum, a little bit further. I'm going to hit enter. And I'm going to say, it's somewhere in there. Hit enter. Okay, so there's that maximum right there. Okay, and we could actually use that as one of our points in order to graph this function. I could have plotted negative 2.7, 0.53, but it's pretty close to the points I already have over there. What I am going to use that for, though, is my domain and range. I'm going to write that down here in a second. I'm starting to run out of room. So that is that local maximum. I'm going to do the same thing. I'm going to find that local minimum. So number 3. And I'm going to go over to that other side. I don't want to go too far because I want to be a left bound. There I am right on the left of that. That's pretty good. I'll go just to the right of it. Hit enter. Go back and just give it a guess. Just make sure you stay within those bounds. All right, and there's that maximum. So what I'm going to do is I'm going to use these to name my range in a second. Okay, name my range in a second using those. Okay, so first let's talk about domain. The domain of this function is all real numbers except for where that vertical asymptote is. So the domain is all real numbers but -1. The range is going to be all real numbers from -infinity up until this guy right there, up until that local maximum. Okay, these are called extrema. So we're finding the two local extrema here. So we have the y value is what we're interested in, not the x value, because we're talking y values here. 0.536. I'm going to go to the thousandth. Union. Okay, and actually, this is kind of open for debate. I'm going to put a bracket here even though I'm rounded, because I'm trying to show that this is an actual point on the graph. I'm just rounding it here. And then I'm going to go from that point, from our local minimum there, to positive infinity. So that is 7.464, and then to positive infinity. Now, if you left these as parentheses here, like I said, I think that you could argue either way. I've rounded, so it really doesn't equal that. Personally, I like the brackets. If you left it as parentheses, I wouldn't mark that wrong. All right, but that is how we graph a function that has a slant asymptote. And remember, that happens when the numerator is bigger than the denominator by a degree of 1. And those are really the only type that we're going to be dealing with here this year, is when they differ by degree 1.